In this section, we're going to study circular trigonometry instead of right triangle trigonometry. The two are related, as you will see. And what we have are angles that will be drawn in what's called a standard position. Now, these angles are going to be superimposed on a rectangular coordinate plane. So let me demonstrate here. This will be our y-axis, and this will be our x-axis. And the angle has an initial side on the positive x-axis. So the initial side is what we call the starting side. And then it proceeds in a direction that is a rotation counterclockwise. And then the other side of the angle is called the terminal side. That's where the angle stops. So that's terminal is just a fancy word for stop. Right? And so we see a 50-degree angle that's pictured there. The next angle is a 90-degree angle in the middle. That would be where the initial side is on the positive x-axis and the terminal side, or the ending side, is on the positive y-axis. An obtuse angle on the right will terminate or have the terminal side in quadrant 2. Let's remember what the order of the quadrants are: 1, 2, 3, and 4. Notice that the quadrants also proceed around the central point in a direction that is counterclockwise. So if we have an obtuse angle, that terminal side is in quadrant 2. All right, now we're going to study mostly, at the beginning here, angles that are not multiples of 90 degrees. Those are going to be special because our multiples of 90, 90, 180, 270, 360, they're all going to be angles that fall in between quadrants as far as the location of the terminal side. So they're going to have what's called a reference triangle. So for that 50-degree angle, the reference triangle is formed by taking that terminal side and making that the hypotenuse, and then dropping from there, from the endpoint of the terminal side, down to the x-axis, and the adjacent side, or the horizontal side, will be on the x-axis. Same thing for the obtuse angle, which is on the right here. Our terminal side is the hypotenuse, and we go to the drop down from that endpoint to the closest x-axis, and then the other leg of that right triangle is on the x-axis. Now, 160 and 20 are supplementary angles because when we're in quadrant 2, those two angles form a straight angle. And so 20 is the angle inside the reference triangle, and that is found by taking that 160 and subtracting from 180. Now, we're going to label sides A, B, and C in each of these triangles. And A will be the horizontal side, B is the vertical side, and C is the hypotenuse. And these are related to the coordinate of the point, the coordinates of the point at the end of the terminal side, A comma B. Now you can think of it as X comma Y, but I like to use A comma B because A, B, and C are what we use in the Pythagorean theorem for sides of a right triangle. All right, so what we're going to notice is for the first quadrant picture, the 50-degree angle, A, B, and C are all positive. In the second quadrant picture, A, the x-coordinate of the point A comma B, is a negative number. Okay, B and C are still positive. All right, in the picture down below here, we consider that 8, 15, 17 right triangle that's shown to the right. The endpoint of the terminal side, which is on the circle, is at the point 8 comma negative 15. So that means that from the origin, we have to go right 8, down 15 to get to that point. So we're going to consider the adjacent side, or the horizontal side, to be of length 8, and the opposite side to that reference angle, or the vertical side to be negative 15 in length. So we're going to give a directed distance, negative indicating that it is hanging down from the x-axis. So that means that our hypotenuse is 17. Okay, so let's take a look at some of these statements over here. I want you to notice something about A. A, which is the x-coordinate of the point, is going to be negative whenever we are in quadrants 2 and 3. That is to say that our x-coordinate is negative when we're on the left of the origin, so in quadrants 2 and 3. B, which is the y-coordinate of that point, will be negative whenever our angle terminates in quadrant 3 or 4. That is to say, whenever the terminal side of the angle is below the x-axis. So that would be in 3 and 4. The length of the hypotenuse is always considered to be positive. That's really important to remember. The Greek letter theta that represents our angle is often used to represent angles in trigonometry, and so we'll use it to represent many of these angles. What I do want you to notice, though, is that theta has a vertex that is the origin, or right at 0, 0, and I also want you to notice that the reference angle also has a vertex at the origin. In example 1, we're sketching angles in standard position along with its associated reference triangle, labeling our sides with A, B, and C values, and then finding the other two trigonometric ratios for theta. Okay, so in any standard position angle, the initial side is always on the x-axis, and since this angle has a theta value that is between 0 and 90 degrees, it must terminate in quadrant 1. So I'm going to draw a terminal side in quadrant 1 and sketch in our angle theta. That's a directed angle that goes counterclockwise from the initial side to the terminal side. And now I'm going to draw an associated reference triangle. So our associated reference triangle is formed by utilizing that terminal side as the hypotenuse, and then taking the endpoint of the terminal side and dropping a horizontal to the nearest x-axis. That'll form our opposite side, and the horizontal or adjacent side will be on the x-axis. So if we look at our picture, theta is that angle that has a vertex at the origin. Sine of theta is opposite over hypotenuse, so our opposite side can be 3, and our hypotenuse can be 5. That's a 3, 4, 5 triple, so that makes the missing adjacent side 4. And then we can find the values of the other two trig ratios. So cosine of angle theta is equal to 4/5 adjacent over hypotenuse, and tangent of angle theta is equal to 3/4 opposite over adjacent. In B, we have an angle that has a value that is somewhere between 180 and 270 degrees. So again, our initial side is on the x-axis, and if we think about 0 degrees being represented by the initial side, 90 degrees if we rotate up to the positive y-axis, 180 degrees if we rotate to the negative x-axis, and 270 degrees if we rotate one more quadrant. That means that our terminal side is going to fall somewhere in the third quadrant between 180 and 270 degrees. This is our angle theta, which is an angle bigger than 180 degrees. Next task is to draw our reference triangle. So the terminal side becomes the hypotenuse, and from the endpoint of the terminal side, we find the nearest x-axis, and then the horizontal side is on the x-axis. The angle that's inside the triangle is called the reference angle, and I didn't write that very clearly, but that says theta with a subscript of REF for reference. So we're going to use that reference angle for referring to positions like opposite and adjacent. So what I know is that cosine of angle theta is negative 5/6. So cosine is adjacent over hypotenuse. Now, if a ratio is negative, that means that either the numerator or the denominator could be negative. In this case, I knew the numerator had to be negative because our adjacent side is pointing to the left. And the hypotenuse, by the way, always has to be positive. This is not a triple, so we're going to use the Pythagorean theorem. Negative 5 squared plus b squared is equal to 6 squared. Negative 5 squared is 25, and 6 squared is 36. That gives us b squared is 11, and b is, if you remember from quadratic equations have two solutions, so if we take the square root on both sides and include the positive or the negative solution, b is either equal to the positive square root of 11 or the negative square root of 11. If we look at the picture, that vertical side is hanging down from the x-axis, and the endpoint of the terminal side is in quadrant 3 where both coordinates are negative, so that means that that opposite side will have a directed length of negative square root of 11. Once we have that picture drawn, then we can find the value of the other two trig ratios. So we were given cosines, so we're going to need sine and tangent. So sine of angle theta is equal to the opposite from the reference angle over the hypotenuse, so negative square root of 11 over 6. And the tangent of angle theta is equal to the negative square root of 11 over the negative square root of 5, but that's a negative over a negative, which we need to simplify to a positive. So that's square root of 11 over 5. So the value of the tangent will be positive because it's a ratio of two negative lengths. Your turn to try. In this next one, sine of theta is given to you as 5/13, and the angle theta is between 90 and 180. So sketch your reference triangle and then find the value of cosine of theta and tangent of theta. Pause the video while you do this. Okay, hopefully you got cosine of theta is equal to negative 12/13 and tangent of theta is equal to negative 5/12. A really easy mistake to make on this one is to find the missing side length of 12, but to forget that since that side length is indicative of a point in the second quadrant, that the x value or a value will be negative. All right, let's try D on your own. This is an angle between 270 and 360 where tangent of theta is given as negative 3 over 2. Pause the video while you try this one. Okay, a couple things that are important for this one. It's not a Pythagorean triple, so we do have to use the Pythagorean theorem. 2 squared plus 3 squared is equal to c squared, gives you a c value of the square root of 13. And then for sine and cosine of theta, those will be opposite over hypotenuse, which will put a radical in the denominator, so those will have to be rationalized. So negative 3 over the square root of 13 will be rationalized and become negative 3 times the square root of 13 over 13. All right, moving on. In example 2, we're going to consider very specific angles, and in specific, we'll be looking at ones that relate to special right triangles that we've studied. So we're going to sketch a 60-degree angle, initial side on the positive x-axis, and a 60-degree angle is closer to 90 than it is to 0. As far as where its terminal side is, so that's a 60-degree angle. And then let's sketch in the triangle. Terminal side is the hypotenuse. Drop from there down to the x-axis, and that will give us our opposite side. Adjacent side is on the x-axis. So this is a 30, 60, 90 triangle. The smallest side opposite the 30 is equal to 1. The opposite side, opposite the 60-degree angle, could be the square root of 3 and the hypotenuse 2, right? These don't have to be the numbers, they just need to be multiples of those numbers. So from this picture, sine of 60 is the opposite over the hypotenuse, which is square root of 3 over 2. Cosine of 60 degrees is adjacent over hypotenuse, which is 1 over 2. And tangent of 60 degrees is opposite over adjacent. That's going to be square root of 3 over 1. We will never leave a final answer with a denominator of 1. So square root of 3 divided by 1 is just the square root of 3. So that's in simplified form. All right, let's try B, which is a 135-degree angle. So for this 135-degree angle, again, our initial side is on that positive x-axis. And if we rotate 90, that takes us to the end of the first quadrant. And another 45 degrees will take us into quadrant 2. So this angle is 135 degrees. But as we draw the triangle, the hypotenuse is the terminal side. And we drop from the endpoint of the terminal side down to the x-axis. That will provide us with the opposite or the vertical side, and the adjacent side is, or the horizontal side is on the x-axis. So for a 135-degree angle, that theta reference, or the angle inside of the triangle, is found by subtracting from 180. So 180 degrees minus 135 degrees is 45 degrees. That gives us a 45-degree angle inside of the triangle. So we know from special right triangles that we can label the sides of a 45-45 right as 1, 1, and the square root of 2 for the hypotenuse, but we need to think about negatives and positives. The horizontal side has a negative value because it is directed to the left of the origin. The vertical side is positive because it's pointed up from the origin, and the hypotenuse is always positive. So our value for sine of 135 degrees is opposite over hypotenuse. That's 1 over the square root of 2. That rationalizes to the square root of 2 over 2. The cosine is negative 1 over the square root of 2, or negative square root of 2 over 2. And the tangent is 1 over negative 1. Again, we don't leave a denominator with a 1 in it. 1 divided by negative 1 is negative 1 in simplified form. All right, your turn to try. So pause the video while you try C on your own. Okay, here are the values. Sine of 210 is negative 1/2. Cosine of 210 is negative square root of 3 over 2. And tangent is positive square root of 3 over 3. Notice that the tangent, it has opposite and adjacent sides both negative, so when we write the ratio, it's a negative divided by negative, which is a positive, and then that result will need to be rationalized. All right, let's try D. So try D and pause the video while you try this one on your own. Okay, here's the result for D. Notice when we're in quadrant 4 that 300-degree angle, theta, and the reference angle have to add up to 60 because together they're going to make one full revolution around the circle. Okay, on the next page, we're going to consider angles with terminal sides in each of the 4 quadrants. The reference triangles are always drawn with the horizontal side on the x-axis. That's super important. SOHCAHTOA and the reference angle can be used to find the sine, cosine, and tangent ratios for each angle. So for quadrant 1, if we have an angle theta, drawn in standard position, then we drop from that endpoint of the terminal side to the horizontal axis and form a reference triangle with sides of A horizontal, B vertical, and C hypotenuse. And in quadrant 1, the reference angle is the angle inside the triangle, so it's the same as theta. So no fancy footwork there to figure out a reference angle. In quadrant 2, if we go to the endpoint of the terminal side and drop a vertical there, and horizontal side is on the x-axis, and the hypotenuse is the terminal side, sides A horizontal, B vertical, and C hypotenuse. In this case, our reference angle, which is right here, is found by subtracting from 180. So the reference angle is equal to 180 minus the value of theta, because these are going to be supplementary angles. In quadrant 3, we have our hypotenuse as the terminal side, and we drop to the nearest x-axis, and that horizontal side is on the x-axis, sides A, B, and C. And in this case, our reference angle is inside of that triangle, and theta is the angle that goes beyond 180. So we notice there's a relationship with 180 here, but now theta is the bigger angle. So theta reference is equal to theta minus 180 degrees. In quadrant 4, theta is the angle there that's going counterclockwise around that circle. Hypotenuse is the terminal side. From the endpoint of the terminal side, find the nearest x-axis, and then draw the horizontal side on the x-axis. Sides A horizontal, B vertical, and C hypotenuse. And our reference angle is right there inside the triangle. Notice that those two angles add up to a full revolution, or 360 degrees. So that means that the reference angle, theta reference, is equal to 360 degrees minus theta. Okay, let's notice that for each of these triangles, there is a consistent definition here. B is always opposite the reference angle, and A is always going to be our adjacent side. So if for an angle that is drawn in standard position, where the endpoints of the terminal side are 0, 0, and A, comma B, sine of angle theta is equal to opposite over hypotenuse. Cosine of theta is equal to adjacent over hypotenuse. And tangent of theta is equal to opposite over adjacent. And if we know A and B, then C can be found by using the Pythagorean theorem. C is the square root of A squared plus B squared. Now, the reason that we formalize these definitions here is that they can be used to fill in the gaps in what we can do when we draw reference triangles. For angles that are a multiple of 90 degrees, it's easier to use those circular definitions since it's not actually possible to form a reference triangle for those angles. It's a hint here is that for every quadrantal angle, that's what we call angles whose terminal side fall in between the quadrants, or terminal side is on the axes, either A or B will be a value of 0. The other coordinate may be positive or negative, but its specific value doesn't matter. All right, let's take a look at these quadrantal angles. Given its measure, we're going to find the value of all three trig ratios if possible. All right, so an angle of 90 degrees. Here's our x-axis and our y-axis. And for an angle of 90 degrees, it will have a terminal side on the x-axis and a horizontal it'll have a initial side on the x-axis and a terminal side on the positive y-axis. The endpoint of the terminal side has coordinates, and what we know about that point is it has an x-coordinate of 0, and its y value is positive. Doesn't matter what value is, so I'm going to use the easy number 1. And if we know that those are our A value and our B value, A is 0, and remember, that's the adjacent side, and B is 1, and that's going to be the value of our opposite side. If we want to find the value of C, we can use the Pythagorean theorem. A squared plus B squared is equal to C squared. And that's 0 squared plus 1 squared is equal to C squared. 0 squared plus 1 squared is 1. So that's going to give us a hypotenuse of 1. Remember, the hypotenuse always has a positive length. So sine of angle theta is equal to the opposite over the hypotenuse, which simplifies to 1. Cosine of angle theta is equal to the adjacent over the hypotenuse, which simplifies to 0. And tangent of 90 degrees. Actually, I should be probably specific here, and instead of writing sine of theta, write sine of 90 degrees, cosine of 90 degrees, and tangent of 90 degrees. Tangent is opposite over adjacent. That's going to be 1 over 0, and remember that that is undefined. All right, now let's find the values of sine, cosine, and tangent for 180 degrees. So that's also a quadrantal angle. And for a 180 degree angle, our initial side's on the positive x-axis, and a terminal side is going to be on the negative x-axis because this is a half turn, 180 degrees. The end point of that terminal side is right over here. Its coordinates are an a value or an x value that's negative, so I'm just going to write -1 there, and a y value or a b value that's equal to 0. So a is -1, that's our adjacent side. B is 0, that's equal to our opposite side. And the Pythagorean theorem is going to work pretty much similarly here. -1 squared plus 0 squared is equal to c squared. That's 1 plus 0 is equal to c squared. That's going to give us a c value of 1 again, so c is the hypotenuse. And the sine of 180 degrees is equal to the value of the opposite over the hypotenuse. That's going to be 0. Cosine of 180 degrees is equal to the adjacent over the hypotenuse. That's going to be -1 over 1, which is -1. And the tangent of 180 degrees is opposite over adjacent. 0 divided by -1 is 0. All right, time for you to try 270 degrees. All right, hopefully you got -1, 0, and undefined as the values of the three trig functions. One last one for you to try, so pause the video while you try this for 0 degrees. For 0 degrees, it's important to recognize that there's no rotation, and therefore initial sides and terminal sides are concurrent. So the endpoint is 1, 0, which gives us an adjacent of 1 and an opposite of 0, and then our hypotenuse is again 1. So hopefully you found values of 0, 1, and 0 for those three trig functions.